Hello. In this video we're going to look at a classic discrete Markov chain. The particular Markov chain that we're going to look at was one of the early problems that stimulated the field. The problem it was designed to resolve is often referred to as the gambler's ruin problem. As such, by the end of this video, you should thus be able to write out the transition graph and transition matrix for the gambler's ruin problem, classify the states in the gambler's ruin problem as transient/recurrent, use conditional probability to obtain a difference equation, the solution of which tells one the probability of ruin, and use condition expectation to obtain a difference equation, the solution of which tells one the length of the game in gambler's ruin. As variety is the spice of life, we are not going to consider the classic gambler's ruin in this video. We are instead going to think about a related problem involving the game of tennis. I would like you to consider a game of tennis that has reached deuce. In this game, the server has a probability of winning each point that is equal to p. Furthermore, from deuce, he must win 2 consecutive points in order to win the game. If the server wins 1 point, the score moves to advantage server. If he then loses the next point after he has gained this advantage, the score moves back to deuce. The same holds true for the returner. He must win 2 consecutive points in order to win the game. If he wins 1 point from deuce, the score moves to advantage returner. If he loses the next point, however, the score moves back to deuce. Furthermore, the returner has a probability of 1 minus p of winning any point because the server has a probability of p of winning the point. Given this description, I would like you to pause the video for a moment and explain on a piece of paper why the score in the game can be modelled using a discrete Markov chain. I would then like you to write out the transition graph for this chain and to identify the transient and recurrent states. Lastly, try to note down whether the chain has a limiting stationary distribution or not. Pause the video and do this exercise now. The process is Markovian because the future value of the score, at least in the description, only depends on the current value. We have in this question neglected any psychological advantage/disadvantage that might come from winning or losing the previous point, and simply stated that the server has a probability of p of winning the point. This is why the process is Markovian. The transition graph for this Markov chain looks something like this. There are 5 states in this chain. State 0 corresponds to a win by the returner. State 1 corresponds to advantage returner. State 2 is the state we started in, deuce. State 3 is advantage server. And state 4 is a win by the server. One of the 2 players, server or returner, will eventually win the game. At this point, the score stops changing. As such, states 0 and 4, returner wins and server wins respectively, are recurrent. States 1, 2 and 3, meanwhile, are transient, as at some point in the future the chain will cease to visit any one of these 3 states. Furthermore, because the chain has a mixture of transient and recurrent states, it has no limiting stationary distribution. Ultimately, the game will end with a win for the server or the returner, so we will finish in either state 0 or state 4. The transition graph shown in this slide is an example of what the transition graph looks like for the gambler's ruin problem. The difference is that the typical gambler's ruin problem talks about a chain with n+1 states. But just as with the 5-state example shown as the top of this slide, the kth state is connected only to the k+1th and k-1th state, and the 0th state and the end state are recurrent, while the n-1 states between these 2 states are transient. The gambler's ruin chain is used to model the outcome of a gambler repeatedly playing a simple game of chance, such as roulette, in which he repeatedly places a small stake on the outcome. The probability of winning each of these individual games is a constant p, and if the gambler wins, the amount of money in his possession increases as he wins back his stake and more. If, by contrast, the gambler loses, he loses his stake, and thus the amount of money he possesses decreases. The interesting part of the problem is not what happens in each of these individual games. Instead, the aim is to study the aggregate outcome from many games, and in particular to work out the probability that the gambler will lose all the money he walks in with, the probability of ruin. In the chain, ruin is represented using the state 0, i.e. the gambler entering a state where he has £0. There are then a ladder of states that run up to state n, which is the gambler's target. That is to say, the gambler wants to win n pounds by repeatedly making small, let's say £1 bets. As the gambler plays repeated games, the amount of his money in his possession changes, or, in the language of Markov chains, the system hops around the various states. Furthermore, the game only ends when he has £0 left, or when he reaches his target of n pounds and leaves the casino in triumph. That is to say, the game ends when we arrive in state 0 or state n. In problems of this type, what we are asked to calculate is the conditional probability that the gambler will be ruined given that he arrived in the casino with k pounds to his name. In the remainder of this video, I will refer to these conditional probabilities for ruin using the symbol πk, as shown above. Thus, π0 represents the probability of ruin given that he entered the casino with nothing. π1 is the probability of ruin given that he entered the casino with £1, and in general, πk is the probability of ruin given that the gambler entered the casino with k pounds to his name. We have already seen how to calculate these conditional probabilities in the video on hitting times and probabilities. In that video, we partitioned the transition graph into transient and recurrent states, and then did some simple matrix algebra. What is particularly interesting about the gambler's ruin problem, however, is that we do not need to proceed via this route. We can instead find the conditional probabilities by solving a difference equation, which is useful as it ensures that we can solve the problem for a general chain containing n+1 states, where n is any integer. I will provide an exercise that takes you through this process, but in this video I want to instead focus on the first stages of the problem. That is to say, I want to focus on the difference equation that we will need to solve. Let's thus begin the derivation of the equations that we will need to solve. Let's begin by working out the values of π0 and πn. n equals 4 in this case, as we are considering a 5-state chain. These are trivial to determine. If the gambler enters the casino with no money, he cannot gamble, and thus cannot increase his state. In other words, if he starts in the ruined state, he will remain there forever. π0 is thus equal to 1. By a similar logic, if the gambler enters the casino with n pounds, his target, he has no need to gamble. He already has all the money he desires. The probability that he will thus be ruined, πn, is thus equal to 0. Let's now turn to the calculation of π1, π2 and π3. We can make progress in calculating these quantities by recalling the partition theorem that we learnt about when we were first studying conditional probability. We can calculate the value of the random variable, i.e. random variable y that tells us if the gambler is ruined at the end of the session or not, by conditioning on a second random variable, capital X. In this case, this second random variable, capital X, will be the outcome of the first game, which will have a value of 0 or 1, as the gambler will either win or lose this first game. The partition theorem tells us that the probability y takes a particular value, i.e. the probability of ruin, can be calculated using the expression shown here. We can read all of the quantities in this expression from the transition graph, as I will now show. Let's suppose that we start in state 2. The probability Py, that we would like to calculate is thus the probability of ruin given that we started in state 2, pi 2. The left-hand side of this equation is thus equal to pi 2. The random variable capital X tells us about the outcome of the first gamble. This will be a win or a lose. Furthermore, we know that a win, x equals 1, occurs with probability p. The probability that x equals 0 is thus equal to 1 minus p, while the probability that x equals 1 is equal to p. Now what about these conditional probabilities, the probability of y given x equals 1 and the probability of y given x equals 0? Well, these tell us the probability of ruin given that he loses and wins the first game respectively. The process is Markovian, however, and so the outcome of the first gamble does not affect the outcome of the second gamble or anything that happens subsequently. The only thing that will affect what happens in the future is the amount of money that he has left. Consequently, if he loses the first game, he now has £1 only. The probability of y given x equals 0 is thus equal to pi 1. If, by contrast, he wins the first game, he now has £3, and the probability of y given x equals 1 is equal to pi 3. You can think of it like this if you like. Once he placed the first game, it no longer matters. The only thing that changes is the amount of money he has. The conditional probabilities of being ruined, given that you are in each state, are constant throughout. The state the gambler is in, however, represents how much money he has, and this will therefore change randomly with time. By putting all these realizations together, we arrive at the homogeneous difference equation shown at the bottom of the slide. It is this that we will learn how to solve during the exercise. Furthermore, to do so, we will exploit the boundary conditions that we derived at the start. Consequently, before moving on, pause the video here for a moment and take some time to ensure that you understand how all the equations on this slide have been derived. Perhaps unsurprisingly, the other gambler's ruin problem that comes up regularly involves determining the expected number of times the gambler gambles before either winning or losing all his money. I say this is unsurprising, as when we looked at these chains with mixtures of transient and recurrent states, we talked about calculating hitting probabilities, which we have already seen how to calculate in this case, and hitting times, which we have not yet seen how to calculate. Once again, for the gambler's ruin problem, we can exploit the theory of difference equations and thereby avoid performing the matrix inversions which we saw were necessary for calculating hitting times in previous videos. Furthermore, much as in the previous slides, solving these difference equations gives us a general expression that holds for chains like this one, but with an arbitrary length, n+1. On this slide, I am again going to focus on the setup of the problem. I will leave generating a complete solution to the problem to the exercise. With this in mind, let's introduce some nomenclature. I will use the symbol dk to indicate the expected number of gambles the gambler will make, given that he entered the casino with k pounds to his name. Notice that there is one dk value for each of the states in the chain, and much as was the case for the probabilities on the previous slides, determining d0 and dl is trivial. If the gambler enters with no money, he cannot gamble. And if he enters with his target amount of money, he will not gamble. d0 and dl are thus equal to 0 as a reflection of these facts. To calculate d1, d2 and d3, we need to exploit the conditional expectation theory. We will exploit a similar vein of reasoning to that we did on the previous slide, and will condition on the outcome of the first gamble here, which the gambler will either win x equals 0 or lose x equals 1. On the left-hand side, let's set the expectation of d equal to dk. In other words, we are calculating the conditional expectation for the length of the game given that the gambler entered the casino with k pounds. The probabilities on the right-hand side can then be read off the transition graph directly, as I have already shown. Having started with k pounds, the gambler will either win the first game or lose the first game. Hence, on completion of the first game, the gambler will either have k minus £1 if he lost, or k plus £1 if he won. Now comes the important point. The outcome of this first gamble will not affect what happens subsequently, as the process is Markovian. The only thing that affects what happens subsequently is the amount of money the gambler has in his possession. We can thus confidently assert that the expectation of d, given x equals 0, equals 1 plus dk minus 1, and that the expectation of d, given that x equals 1, equals 1 plus dk plus 1. In these two expressions, the 1 reflects the fact that the gambler has made one gamble by this stage, while the dk minus 1, or dk plus 1, reflects the uncertainty in the way the remainder of the game will play out. The important thing, however, is that because the process is Markovian, what happens after this first gamble is unaffected by the outcome of the first gamble. In other words, the expected number of gambles that the gambler will subsequently make if he loses the first game, and thus has only k minus £1 left to play with, is exactly the same as the expected number of gambles he would have made had he entered the casino with k minus £1. When everything is combined, we end up with the following inhomogeneous difference equation, which can be solved given that we have the two boundary conditions for d0 and dl. As I have already explained, there will be an exercise to take you through this process, which we will go through in class. To conclude then, you should now hopefully be able to explain the gambler's ruin problem. You should thus be able to use your understanding of this problem to write out the transition graph and transition matrix for the gambler's ruin problem, to classify the states in the gambler's ruin problem as transient/recurrent, to use conditional probability to obtain a difference equation, the solution of which tells one the probability of ruin, and to use condition expectation to obtain a difference equation, the solution of which tells one the length of the game in gambler's ruin problem. There are programming exercises and written exercises that should allow you to fill in the remaining gaps in your understanding of this problem. Try these now and see how you get on. Thank you for your attention.